Okay, we're very happy today to have Matt Rosenzweig from MIT. He will tell us about his new results on point vortices in Euler and the mean field limit. So, thank you, Matt.
Okay, thank you to the organizers for the invitation. It's a great pleasure and privilege to speak at this seminar. So as Vlad said, I'm going to be talking about systems of interacting particles today, primarily focusing on point vortices and focusing on their connections to certain PDE, such as the Euler equation, through scaling limits. So here's a quick outline of the talk. First, we'll start by, in the introduction, introducing point vortices and the relationship to the incompressible Euler equation. And then we'll specialize the discussion to the mean field regime, which is the scaling regime of interest throughout this talk. And then in the remaining portions of the talk, we'll present several different results. The first is on mean field convergence for limiting vorticity measures that can be rough, just essentially bounded. And we'll present the results, comment briefly about the proof, and then discuss some higher dimensional generalizations. And then in the last portion of the talk, we'll discuss what happens when multiplicative noise is added into the picture and what we can say in this setting. And then finally, I'll conclude with just a few remarks about some remaining open questions and possible lines of research for the future. So to get started, the point vortex model is the system of n ordinary differential equations, which is given by equation 1,1. And here, n is the number of vortices. These coefficients a1 through an, which are taken to be non-zero and real, are the circulations, sometimes called intensities of the vortices. x1 naught through xn naught are the pairwise distinct initial positions in the plane. G of x, this mathfrax font, is the two-dimensional Coulomb potential. So in particular, it's logarithmic. And this Nabel perp is the 90 degrees counterclockwise rotation of the usual gradient. And there's something that you should note from the equation in 1,1. It's that a single point vortex is moving only under the velocity fields generated by the other point vortices. You'll notice that the summation excludes when j is equal to I. And this rules out that there's any self-interaction between the point vortices. And then you could ask, well, if n equals 1, what happens? And that means that a single point vortex doesn't move at all. So what's some history about this model? Well, as far as I know, it goes back to work of Helmholtz and Kirchoff in the middle to second part of the 19th centuries. It was the basis of Onsager's statistical theory of 2D turbulence in his famous Nuovo Cemento paper, which was mathematically revisited later by Cagliotti, Jones, Marchior, Polverenti, and Kiesling in the 90s. It's also served as the basis for numerical methods for fluids, treated by a number of people. It's not an exhaustive list. And more recently, I learned that it's been used to model vortices in two-dimensional quantum superfluids. It's been considered in the physics literature for that purposes. But it's also a very interesting dynamical system, a Hamiltonian system, in fact, in its own right. And a nice survey of what's known and open questions about the dynamics of the system is given in a paper by Varef. So what is the connection to the Euler? Well, the point vortex model is an idealization of 2D incompressible inviscid fluid flow. And I think as many people here know, such flow is governed by the Euler equation, which in 2 dimensions can be described by a scalar vorticity satisfying the equation 1, 2. So this first equation is the transport of the vorticity along the velocity field generated by the flow itself. And the velocity u can be recovered from the scalar vorticity through the Biot-Savart law, just by integrating with this vector-valued kernel. Now, how do we connect this to the point vortex system? Well, let's take the empirical measure of the vortex system, which is this counting measure given in equation 1, 3. And I claim that this is a solution to what's known as the weak vorticity formulation of the Euler equation, where it's been written in weak form, but the nonlinearity has been symmetrized so that you can cancel out the singularity along the diagonal. You can think of this as like a renormalization of the nonlinearity, where the renormalization is done by excluding the diagonal. And this is well defined for point masses if you substitute in here. It's just because you're avoiding the diagonal. I think this formulation originates in a paper of Delort, if I'm not mistaken. But so the goal of this talk is to mathematically make sense of a fluid in terms of a large system of interacting particles, in quotation marks, of vorticity. And there are two angles, I think, to this goal. The first is that, well, to what extent is the point vortex system a particle approximation to the Euler equation? And the second is, to what extent is the Euler equation a continuum approximation to the point vortex system? And you can consider either of these angles depending on, or questions depending on what your interest is. Now, our emphasis in answering both of these questions is on quantitative bounds because it's more useful to have an estimate of how close two things are than just knowing that they get close in some asymptotic regime. And given that the empirical measure, which we're denoting by omega n, is already a weak solution to the Euler equation, we expect this to be the relevant object to consider in trying to answer these two questions. But of course, for this line of inquiry to make any sense, we need to consider some sort of scaling regime. There's no reason for there to be any non-trivial dynamics as, say, n goes to infinity if we just consider the point vortex system as given. We need to impose some further constraints. So the constraint we're going to impose is by considering the mean field regime, in which we're passing from the discrete setting, system of particles, to the continuum setting, a fluid PDE. And so in this regime, the number of vortices n is tending to infinity. The vortex circulations are going to be taken to be equal to 1 over n or proportional to 1 over n. You could ask, well, why are we choosing these to be positive? And the reason is because we're limiting our attention to the repulsive regime, where the signs of all the vortex circulations are identical. And now in the scaling, the total circulation is fixed as n goes to infinity. Why was this called, I guess, mean field? Or, well, the velocity field that's experienced by a single point vortex is proportional to the average of the fields that are generated by the remaining point vortices. And in particular, the energy per vortex pair is going to be finite in the limit as n is going to infinity. So the goal is, well, if we assume that our initial data, or more precisely, the empirical measure generated by the initial data to the point vortex system, converges to a suitably regular measure, omega naught, on R2 as n is going to infinity, we want to show that the time-involved empirical measure converges in some weak sense to the solution omega of the Euler equation with initial datum omega naught. Okay?
Matt, can I ask?
Sure.
The vortex circulations, you're taking them all to have the same sign.
Yes.
Is there a reason why the circulations are not?
So that's a good question. So the dynamics are a bit different, non-trivially different, if you have different choices of signs in these circulations. For instance, if all the circulations are identically signed, then the point vortex system is well posed in the sense that the vortices can never merge together. And this follows from conservation of energy and moment of inertia. But if you have different choices of signs, then it's possible to have the analog of finite time blowup, vortices merging together. So the problem is not well posed in that sense for necessarily long enough time scales to consider as n going to infinity. And actually, the physics can be very different if you have arbitrary circulations in the picture. That's a good question.
Thanks.
Sure. Okay. So what's known about this topic? Well, the first result I'm aware of is by Chauchet, and I think that's how it's pronounced, in the mid-1990s. And this assumes that the initial empirical measures converge to some right-on measure, omega naught, in the plane. And it shows that you have weak star convergence of the time-involved empirical measures to some measure-valued solution to the Euler equation along a subsequence. And the proof is based on a refinement of Delort's existence result for h-1 measure-valued solutions. But due to a lack of uniqueness, you can't characterize the limit points. And so in this sense, we'd refer to it as a partial result. You can't really say anything about the solution that you're converging to along this subsequence. And in particular, if your initial data omega naught at the asymptotic level has a little bit more regularity, because there's this lack of uniqueness in, say, h-1, you don't know which solution you're necessarily converging to with that initial datum. But the first complete result was given by Sarfati a number of years later. And this also has the benefit of being quantitative in that you have an explicit rate of convergence for the mean field limit. This is based on rather different arguments. More precisely, the modulated energy method, which she'd introduced in the context of Ginzburg-Landau vortices. And because it's able to characterize the limit point, you need to work with a little bit more regular solutions. So it assumes that you have an initial datum, limiting initial datum omega naught, which admits a solution omega, which has a bounded density, or essentially bounded density. And moreover, that the velocity field u associated with the solution is spatially Lipschitz. If you know something about, well, I guess fluid equations or harmonic analysis, you can see that the second condition is a little bit stronger. That even if the vorticity is an L infinity, that doesn't necessarily tell you that the velocity field is Lipschitz. And we'll circle back to this point later. And then finally, if omega, the initial empirical measures converge to this limiting measure omega naught in some suitable sense, then the time evolved empirical measures also converge to the solution necessarily unique omega of the Euler equation with initial datum omega naught. And I should mention that this work by Sarfati is actually doesn't just treat point vortices. It's the point vortices are actually a special case of a more general family of systems of interacting particles with Riesz interactions. So you can think of these as the generalization of point vortices corresponding to, say like the surface quasi-geostrophic equation and the generalizations of that. So, okay, now on to the first result that we're going to discuss on mean field convergence when we possibly have non-Lipschitz vector fields or velocity fields u. So for motivation, let's recall something about the Euler vorticity equation, which I've reproduced in 2.1. It has the scaling invariance given by equation 2.2, where we rescale the spatial variable x by some positive number lambda. Now, what's interesting about this scaling is that it leaves the L infinity norm unchanged. In other words, L infinity is a critical function space for considering the well-posedness of this equation. And moreover, the L infinity norm is actually a conserved quantity for the Euler vorticity equation. More generally, all the LP norms are conserved. This has to do with the fact that they're a degeneracy known as a Casimir of the Poisson structure underlying the Hamiltonian nature of the Euler equation. And in fact, a famous result of Udovich from the 1960s is that the Euler equation is globally well posed for vorticity, which is an L1 and L infinity. So you have, say, some measure, which has an L infinity density, then there's a unique global solution corresponding to that initial datum. But it's important to note, and I mentioned, alluded to this earlier, that if the vorticity is an L infinity, the velocity field at best is, or we only know that it's log Lipschitz. And by log Lipschitz, I'm referring to equation 2.3. So it's like the Lipschitz modulus of continuity, but there's this logarithmic factor, which spoils it a little bit. Okay. So this leads us to the following question, which is, can we show mean field convergence under the same assumptions as Udovich's result, in particular, treating the case of non-Lipschitz velocity fields and requiring no regularity for the limiting vorticity? So nothing, say, better than L infinity. And this leads us to our first theorem that we'll talk about, which is answering this question. So you can sort of ignore the top that's appearing above. I don't think that's so important. We're dealing with solutions omega, which are measure valued with L infinity density and some technical conditions on them. And the estimate that we shown in 2.4 is a bound on the Sobolev norm, HS, for s less than -1, of the difference between the empirical measure omega n and the limiting vorticity omega. And has this complicated right-hand side that we'll comment on momentarily. The first two terms over here, or this term here, okay, that's small as n's going to infinity. That's also small as n's going to infinity. Well, what's happening right here, this Fn, which I'll talk a little bit about more later, is this quantity defined in equation 2.5, which is a pseudo distance measuring how close the initial empirical measure is to the initial datum of the Euler equation. And if you look at equation 2.5, you can see that this looks very similar to the Coulomb energy of omega n naught minus omega naught, except we've excluded the diagonal in the integration. And the reason, again, is because, well, the point vortices don't make sense along the diagonal. You have this infinite self-interaction. We'll comment a little bit more about the relevance of this quantity right here momentarily. But of course, if this Fn is going to 0 as n goes to infinity, then we can deduce by standard arguments from the bound given in 2.4 that in fact the time-evolved empirical measure is converging in the weak star sense to the solution omega of the Euler equation. Okay. So the important takeaway here is that the only thing entering the picture is that the vorticity is an L infinity. So some brief comments on the theorem before we talk about its proof. There's some technical conditions, this mild decay assumption on the initial datum, which are qualitative. They're not really that important except to ensure that the Coulomb energy is well defined and the potential of the vorticity is also well defined as well. It's like a logarithmic growth condition. The more interesting thing, though, is that we don't actually need to assume that the vorticity is an L infinity initially. It suffices for it just to be an LP for some p bigger than 2, with the caveat that we have an a priori bound on the log Lipschitz norm, semi-norma view. I mean, that's really what's important here, is that the velocity is in log Lipschitz for our proof. So related to this quantity Fn that we saw earlier, when does it actually go to 0 as n goes to infinity? It was observed by Dweringks that if you have weak star convergence of the initial empirical measures to the initial datum of the Euler equation, and you have convergence of the energies, then that implies that this quantity Fn also tends to 0 as n is going to infinity. So that's those are sufficient conditions for that to hold. And then the last remark is that we're working at the level of the empirical measure, but if you instead worked at the level of the Euville equation, so you're corresponding to randomizing the initial datum at the m-body level, then you also have propagation of chaos, which means that if your solution to the Euville equation is initially factorized, so the distribution of the particles or the point vortices they're identically independently distributed, then all the k particle marginals have to asymptotically factorize as well.
Matt, may I ask you another stupid
question? Sorry. Before I comment, it was just pointed out to me. Yeah, there's a small typo in the left-hand side of actually a slightly big typo on the left-hand side of equation 2.6. Ignore that grad perp there. It should just be the g evaluated xi naught minus xj naught. Yeah, sorry. Go ahead, Vlad.
Is there a notion for the point vortex system? Is there a notion of kinetic energy? And if so, what happens to it when capital N goes to infinity?
A notion of kinetic energy.
I mean, I noticed that your convergence theorem does not hold in h-1, which is the level, h-1 norm of the vorticity would be the level of the kinetic energy converging, which is the L2 norm of the velocity.
L2 norm. So ignoring this grad perp at the point vortices, this is the energy.
Not on this slide, on the previous slide.
Okay. Let me go back.
You see, omega n minus omega converges in spaces which are below h-1.
Yeah.
But that's because the Diracs are not in H-1, right?
Exactly.
That's the reason.
So that you can't be.
So that's why I was asking if there's kind of a renormalized way to define a kinetic energy, but I guess there isn't.
Well, I mean, well, as we'll see, this quantity Fn is in some sense a renormalization of the H-1 norm.
Okay.
And the renormalization has to do with to remove an infinite self-interaction.
Okay. Thank you.
Sure. Okay. Yeah. So there's that typo.
Is this result, sorry to interrupt, is this result of Dirichlet's, is this quantitative or is this really soft like you stated it?
So in the sense like, can you get an exact rate on how quickly Fn is converging?
Yeah, like if you have rates for the top two, do you get a rate for the bottom one?
I don't know off the top of my head. I don't, off the top of my head, I don't know. I'd have to check.
Okay. Thanks.
Yeah.
And also on this slide, when you talk about the a priori bound on the log Lipschitz seminar, you have it for all time, right? You need to assume it for all time. It's not just.
Yeah. So say like you fix some compact time interval, and then you need the log Lipschitz semi-norm to be bounded on that time interval.
But so that's a pretty strong assumption.
Yeah, it would. And well, it's implied if the vorticity is an L infinity, but I don't know of another. I'm not sure off the top of my head what would be a weaker assumption on solely the vorticity that would imply that. Weaker than L infinity, I'm saying.
And do you really need log Lipschitz, or is it enough to have some, that the ODE is well posed somehow, is unique?
So for the proof, the fact that the velocity is log Lipschitz plays a role. But I don't know if you were able to modify the proof to remove that, because I think maybe you're hinting at there are log Lipschitz velocity has related to uniqueness results for ODEs. And of course you can relax the log Lipschitz assumption and still have uniqueness. And of course there are results for the Euler equation itself on uniqueness when the velocity field is slightly weaker than log Lipschitz. But for this proof, the log Lipschitz assumption does play a role. Is it okay if I move on? All right. So a quick overview of the proof. It's based on this modulated energy method, which I mentioned earlier in the context of Servati's work. And this is a powerful method. In this context, it exploits a weak, strong uniqueness principle for the Euler equation. And its advantages are that it's quantitative. And in particular, we don't need to have a detailed understanding of the microscopic dynamics in terms of the trajectories of the point vortices. That can be quite hard. I think one of the disadvantages, or at least historically, is that it requires some regularity for the solution of the mean field equation, or say an a priori assumption on it. So, if you had assumed that the vorticity were, say, a little bit better than L infinity, like a Holder condition, then of course that would imply the velocity were Lipschitz. But that's imposing some regularity on the vorticity. So the idea behind this approach is to consider as modulated energy this quantity Fn that was introduced earlier. So it's like the Coulomb energy of omega n minus omega, except in the integration, you're removing the diagonal of R2 cross R2 to exclude the infinite self-interaction between point masses. And as commented earlier, you can think of this as like a renormalization of the H.-1 norm of omega n minus omega, so as to remove this infinite self-interaction. So the idea behind this method proceeds by the energy method. You want to try to prove a Gronwall type inequality for the modulated energy. And why is this modulated energy useful? Well, it in fact controls the H minus S norm for any S less than -1 up to some small additive error, which is vanishing as n goes to infinity. And once you have this control on the HS norm, you can deduce weak star convergence by standard arguments. So driving in a little bit more, well, the time derivative of the modulated energy is given by this equation in 2.8. So here we have the gradient of the Coulomb energy or the Coulomb potential, and we're dotting it against this velocity field UTX minus UTY. And then, of course, integrating against omega n minus omega on R2 cross R2. Now, suppose for a moment that the velocity is spatially Lipschitz. So you can show, with a bit of hard work, that what's in 2.8 is controlled by some constant, which depends on the L-infinity norm of the initial vorticity and on the Lipschitz norm of the velocity field, say on some compact time interval. So you have this additive error term, and then, of course, the modulated energy itself. And once you have this, you can conclude by a Gronwall argument. But the hard part is in removing this Lipschitz assumption. And this is where the new idea comes into play. So the workhorse of our proof is this proposition, which I apologize is a bit of an eyeful. The idea, though, here is that we have some bounded log Lipschitz vector field and some measure mu, which has an L-infinity density. And okay, so this quantity is like we had before. It's just written slightly differently. And you can ignore, I think, everything except this first term right here. I think this is what's important. You'll note that we have the modulated energy again, this Fn, but we have this logarithmic factor, this ln of epsilon 2, where epsilon 2 is going to be some small parameter. And you have all these floating parameters around, this epsilon 1, epsilon 2, epsilon 3, and these are introduced because they allow us to balance terms in order to get something that we want. But this first term here is really, I think, the meat of this inequality. So what is the idea here? And then I'll comment momentarily on how one chooses these parameters. Well, the proof of proposition 2.2 involves several steps, but focusing on the first step, which is a new mollification argument, which was inspired by earlier work I did on a little paper on the mean field limit of the one-dimensional delta Bose gas, which some of you may know has the mean field equation as the nonlinear Schrodinger equation in one dimension. So the idea here is to replace the velocity v in the left hand side of equation 210 by a mollified vector field v epsilon 2. So epsilon 2 is the same parameter as before. Taking the velocity and we're convolving it with some standard approximate identity at scale epsilon 2. So we want to use the log Lipschitz regularity of v to bound the error we get when we do this replacement. We replace v epsilon 2 or v by v epsilon 2. We can get quantitative control on that error using the log Lipschitz regularity. And then we proceed in the proof working with this velocity v epsilon 2, which has been mollified. We avoid any estimates that require the Lipschitz norm of v epsilon 2. However, there's one place where this cannot be avoided, and we have to pay a price, which is we have to take the L-infinity norm of the gradient of v epsilon 2, and that leads to this logarithmic factor right here, the ln of epsilon minus 2, or epsilon 2. Okay, and since I told you that epsilon 2 should be something which is you think of as small, that's not so good having something large there. So what saves the day? Well, if we apply this proposition here, which I told you earlier was our workhorse, pointwise in time. So we're applying it to the time derivative of the modulated energy pointwise in time. And we're allowing these parameters epsilon 1, epsilon 2, and epsilon 3 to depend on time and n through the modulated energy itself, more precisely on the size of the modulated energy. So takeaway is that the rate of mollification is depending on the size of the modulated energy itself. And after some simplification, and this is kind of in caricature, this leads to an integral inequality for the modulated energy given by equation 212. So, okay, you have what you would think in a Gronwall type argument, except when we go down to this integral term, we have this logarithmic factor where the logarithm is of the modulated energy. So okay, the presence of this logarithmic factor rules out applying the Gronwall-Bellman inequality that we teach in ODE courses. But there's a generalization of this inequality, which is quite useful, and that's the Osgood lemma. And this modulus of continuity, which is appearing here, satisfies the Osgood condition. And so we can apply this lemma to get a closed estimate. So if you don't actually care about point vortices or their connection to the Euler equation, I think there's a moral to take away, which is that you don't always need something that's in the form of the Gronwall lemma. It's good enough to have something which still satisfies the Osgood condition, and that will allow you to get a closed estimate. Okay. So I think that's all I wanted to comment on the proof for the two-dimensional case. There's a higher dimensional generalization that you could ask about. So these are systems with Coulomb interactions that we're again considering in the mean field regime, but now the dimension is bigger than 2. So what changes? Well, okay, we have, it's similar as to before, but we have our initial conditions are now in RD, and J is going to be a D by D skew symmetric matrix with real entries. And of course, the Coulomb potential is changing since we're in higher dimensions. So for the same reasons as before, we expect that the empirical measure of this Coulomb system 213 is converging to a solution omega of this PDE described in 214. That looks very similar to the Euler vorticity equation, except we're in higher dimensions, and the Biot-Savart law is a bit different. And oh, I'm missing a convolution with omega there. My apologies. One thing I should emphasize is that this is not 3D Euler, or the vorticity for 3D Euler, for several reasons. First, okay, this is a scalar omega, whereas the vorticity for 3D Euler is a bona fide vector. And also, you would be missing a vortex stretching term. So this is a very different object. And I'm going to skip over this theorem right here in the interest of time, because I want to move on to the noisy case. The punchline is that, okay, we can do something similar as before, but we need some stronger conditions. You need a stronger condition on the size of the modulated energy initially. And also, this estimate is only valid for short times based on what we have so far. It's an open question whether you can extend it to longer times. I suspect this short time restriction is purely technical in the sense that it's just a defect of the proof. It stems from an inefficiency. But the argument given would need to be modified in order to overcome it. So I'm going to skip over that, and I'm going to move on to discussing what happens with multiplicative noise. So I think this is quite interesting. So in recent years, there's been a strong interest in stochastic analogs of well-known fluid models. I think an indication of which is given by some very nice lecture notes by Flandoli from a few years back. And such stochastic analogs are more realistic, you could argue, because, okay, you're incorporating uncertainty through the noise. But as mathematicians, we may be more interested in the fact that they have interesting, or they may have interesting regularization properties compared to their deterministic counterparts, so-called regularization by noise. And motivated by this latter prospect, Flandoli, Gubinelli, and Pirola in around 2011 proposed a stochastic point vortex model with multiplicative noise. So this is given by equation 3.1. So, okay, this is as before in the deterministic model, but we've added in this noise term over here where we have these smooth divergence-free vector fields, sigma k, and these independent real-valued Brownian motions, wk, and the Stratanovich product, which is denoted by this circle right here. So this is like a random transport of the point vortices by these external vector fields, sigma k. So again, similarly as to the deterministic case, if we look at the empirical measure xi-n, where I'm now using the xi as opposed to omega, because I guess in probability the lowercase omega is often used to denote an element of the sample space. This empirical measure is a weak solution to a stochastic Euler equation with multiplicative transport type noise. So this is given by 3-2. Okay, we have what we had in the deterministic case, except now we have this stochastic term right here, where it's sigma k dot the gradient of the scalar xi, and then the Strutanovich product against white noise there. So the Strutanovich equation is formally equivalent to an Ito equation, and that's given by 3-3. So we pick up these corrections on the right-hand side, and here the colon denotes the Frobenius inner product for 2x2 matrices. And in fact, the mathematical interpretation, or I guess work on this stochastic Euler equation is based on this Ito formulation in 3-3. And in fact, using this formulation, Brezhniak, Fuandoli, and Morelli proved an analog of the Udovich theorem for the vorticity of the deterministic Euler equation. You have goal well-posedness for initial vorticity in L1 and L infinity. So, okay, based on what we know in the deterministic case and the preceding observations, we can ask the following question. So suppose we consider the system of stochastic point vortices, again in the repulsive setting and in the mean field regime. Does the empirical measure converge in a suitable sense to a solution xi of the stochastic partial differential equation, which corresponds to the Euler vorticity equation, now with the stochastic noise? In some suitable sense, as n is going to infinity. And as far as I know, this question is unanswered. I was reading a survey by Jabin and Wang from, I think, 2017 or so, where it was listed as open. And the only work I could find is this paper by Kogi and Morelli around 2019, which shows mean field convergence starting from the stochastic point vortex system, but with a truncation of the kernel, where the truncation parameter is n-dependent, and it's vanishing as n goes to infinity, but on a length scale which is much larger than the typical distance between the point vortices, which is like n to the -1/2. So in some sense, it's avoiding the essential difficulty of the problem, which is dealing with the singularity of the interaction kernel. So I should comment, though, that there's a difference here between what happens with additive noise, in that there's a persistence of stochasticity as n is going to infinity for multiplicative noise. We start with a stochastic system, and then we end up with a stochastic PDE. This is in contrast to what happens if we look at the point vortex model with additive noise, where now these W tilde I are independent Brownian motions on R2. If we consider instead this system given by 3-4, and then study the convergence of its initial, of the empirical measure converges to a solution of the deterministic 2D Navier-Stokes equation given in 3-5. And this has been rigorously shown by a number of people, beginning with Osada, and then Fournier, Hooray, and Michler, and then most recently by Jabin and Wang. Okay, so that's where additive noise leads to a deterministic mean field PDE, but in the multiplicative noise setting, we have a stochastic mean field partial differential equation. So this leads to the last theorem that I'm going to present, which is that if we take we have a solution to the stochastic Euler equation, satisfying conditions that are very similar to as before. So it's almost surely a measure with an L infinity density. And we look at the unique strong solution to the stochastic point vortex model, then for all n sufficiently large, we have a bound on the expectation of the magnitude of the modulated energy in terms of this right-hand side given over here. So I presented this a little bit differently, not using the Sobolev norm, because it was more complicated using the Sobolev norm. But from this estimate here, we can deduce a bound on the expected HS norm of the empirical measures IN minus xi in any s less than -1. Okay. So what's different here in the stochastic setting? Well, the idea is to try to carry over as much of the modulated energy method now in the presence of noise, because this is a good method and we want to use it. It's quite powerful. So now the modulated energy is a real valued stochastic process, and it satisfies this Ito equation given by 3.7. So this is, okay, again, an Eiffel. My apologies. This first term, you can forget about it. This is the same as in the classical case. We know how to estimate this because we can apply the estimates we had before pathwise in the realization of the noise. The second term here, okay, this is new, but again, this is very similar to what's up here. You know, just call this sigma k dot grad sigma k, call this a new vector field V, and we can apply the estimates we had before pathwise. This third term, this Ito term here, this has zero expectation, okay? So we don't really need to worry too much about this. You could also estimate directly if you wanted. This last term, though, I think is what's difficult, and I've colored in red. So we now are dealing with the second order correction, and we have this more complicated kernel structure appearing here. And it's unclear how to apply the estimates that we had before in order to control this. So in the remaining few minutes, we're going to talk about how one can deal with this term. And in doing so, I think we'll give a maybe slightly different take or perspective on the modulated energy method. So let's take a step back in discussing this bad term, which I've had colored in red. And suppose that we take some vector field sigma, which is smooth, and we're going to define a integral operator, T sub sigma, which is given by integrating with respect to this symmetric kernel K sub sigma, which I've defined in equation 3.9. So I've just taken what was as before, this nabla squared G, and then the Frobenius inner product against this matrix formed by sigma K minus sigma Y tensored with itself. So I claim from considerations of scaling that T sigma sub sigma should be smoothing by 2 orders. So like mapping L2 to H2. And why is that? Well, this term, right, this nabla squared G is like homogeneous of degree -2. And thinking about the mean value theorem, the sigma x minus sigma y is controlled by x minus y. And then, okay, we're going to have to square that. And that's like homogeneous to degree 2. So in physical space, I'm like homogeneous to degree 0. And then thinking about how the Fourier transform changes homogeneity, you could think that this operator is like doing something which is homogeneous to degree -2 in Fourier space. But more precisely, though, to understand the smoothing property, suppose we integrate by parts. Okay, that gives us equation 3.10, where we pick up this operator, this matrix valued operator, grad T sigma grad, and then acting on these quantities right here, the gradient of G convolved with this measure mu, or this test function mu, T sigma should be smoothing by 2 orders in the sense that this matrix valued operator, nabla T sigma nabla, is bounded on L2. So it's an order 0 operator. So suppose that we have this boundedness property. Why is it useful? Well, integrating by parts as before, okay, this leads us to this right-hand side expression in 3.1, where I've introduced this quantity Hn, which corresponds to the potential of the difference between the mean field solutions I and the empirical measure. Now, if the gradient of Hn were in L2, and I knew that this matrix valued operator nabla T sigma nabla were L2 bounded, then I would be done just by Cauchy-Schwarz. But nabla Hn is not in L2. However, it's a good however, not the part however that's followed by something bad. We can smear the point masses a little bit to some small scale A to I. There's a good procedure in the literature already for doing this, I believe originating Sarfati's original work. And using the smearing procedure, we can obtain an approximate empirical measure xi n with the small scale vector parameter eta. And that leads us to define this smeared out Hn quantity here, where we're just taking the potential of xi minus the smeared out measure. And this, it turns out, is in H.1. So its gradient is in L2. And so by Cauchy-Shor's, okay, we can estimate this quantity right here. And this is just the operator norm of nabla T sigma nabla, and then the L2 norm of the gradient of the smeared out HN. And okay, it was observed in the aforementioned work by Sfratti that if you choose these A to I appropriately, then this gradient, the L2 norm of the gradient of the smeared out quantity HN can be controlled by the modulated energy itself up to some small error, which is vanishing as n goes to infinity. So then, okay, what's left though is what about the error that I introduced in this smearing procedure, where I replaced the empirical measure xn by the smeared out empirical measure xn with this parameter eta bar. Well, you can estimate this directly. And again, you can show that this error is controlled by the modulated energy up to some small additive error. So the last little bit I'll leave you with is, I guess, why is this matrix valued operator bounded on L2? So this is a harmonic analysis question. Well, by examining the Schwartz kernel of this operator, you reduce to proving that this bilinear singular integral form defined in equation 314 is bounded on L2 for any choice of coordinates alpha and beta. So this is the kernel as before, and then we're looking at the partial derivative, the second order mixed partial derivative in x and y. But this bilinear form is an example, or I guess more precisely, can be reduced to an example of a class of singular integral forms called Calderon decommutators. These are a generalization of the classical Calderon commutator in one dimension. And the boundedness of such forms was studied by Kristen Journet on a paper from the late 80s. And then more recently, it's been revisited and highly non-trivially extended and generalized by work of Seeger, Smart, and Street, and by Lai. And the type of estimate that we can get for this bilinear singular integral form is given in equation 315. So it only depends on the gradient of sigma in L infinity. So we need sigma to be Lipschitz. And then, of course, just the L2 of mu1 and mu2. Okay. So this gives us the desired boundedness that we were assuming in the last two slides. So that's all I was going to comment about the proof. And then I guess in the remaining minute or so, couple minutes, I'll just comment on some future questions, other lines of research that could be considered. So the first I mentioned is that in the result on Coulomb systems in dimension bigger than or equal to 3, there's this restriction on short times for the mean field convergence. And I think to overcome that, you need a different argument than was given to remove this inefficiency. I think perhaps a more useful way to think about this is, okay, again, you want to do some sort of mollification, but instead to do the mollification not directly in the modulated energy method itself, but to do it at the level of the initial data for the mean field equation, and to use the continuous dependence on the initial data that you have in the local Cauchy theory for that equation. I think that might be a more fruitful avenue of approach. It's been useful in a different context in the study of quantum systems. And again, what worked in the quantum case was in part inspiration for what to try in the classical, but I haven't checked it out yet. The other thing that can be considered is to look at Riesz systems with multiplicative noise. So you replace the Coulomb potential, G, okay, we're looking at the two-dimensional case, with a more singular Riesz potential of the form given in equation 4.1. And the mean field stochastic partial differential equation should be a generalized surface quasi-geostrophic equation, except now with multiplicative transport type noise. So this would be treating the stochastic setting with multiplicative noise that I mentioned was considered earlier by Sfatti. And then more generally, you could ask about deriving effective equations under scaling critical assumptions. In PDE, it's been a hot topic and for multiple different kinds of equations like dispersive and fluid of studying these equations for initial datum in some scaling critical function space. and then, say trying to prove global well-posedness if you can. But it's been less explored. That's been a less explored question, though, when trying to actually derive these equations. And I think, I don't know. I mean, I think a lot of the derivations perhaps can be reduced to scaling critical assumptions, but there's a lot more work would need to be done answering that. And of course, it may just be a case-by-case basis. And then the last thing that I think I'm perhaps most interested in is going beyond the mean field regime. You can think of results in the mean field as being like law of large numbers type results, telling you about the typical behavior in the limit. But okay, you could think again, well, beyond the law of large numbers, I know from probability that there's also a central limit theorem telling me about the fluctuations. And so that means that we could ask similar questions when talking about systems of interacting particles like point vortices. What can you say about these fluctuations? And can you get higher order corrections to mean field theory? This has been considered, I think, in some limited cases for other classical particle systems. Certainly, it's been a very hot topic for quantum many-body systems in recent years. In the context of point vortices, I've seen physics works by Chavanis, I'm not sure how it's pronounced, that I don't profess to completely understand, but still they're very interesting. But I'm not aware of anything that's quite math physics yet. But again, I guess that's not bad because it leaves for future research.
So you mean that the initial data is random and you want to understand the randomness of the how it's propagated? Is that what you mean? When you speak of fluctuations?
Yeah, you could. So, and this is going back to when I mentioned earlier about, I'm not going to be able to find it working at the level of the Uville equation. I guess I should also mention that fluctuations for classical particle systems are recently studied, not for a collisionless model like point vortices, but in the context of the Boltzmann equation by Gallagher, San Ramon, and one other name I'm forgetting.
Our speaker of last week, yeah.
Oh, okay. I think Simonella is the other author. So I think that's all I was going to say. And so I'll stop here. And I thank you for your attention. And yeah, if you have any questions.
Thank you.
Do people